Hi, my name is Jerome Yuan, and the title of this project is the analysis and design of LLC converter in photovoltaic applications. From the title, we can discern our focus, namely that we are generally looking at photovoltaic or PV applications, and specifically at the LLC converter, which is a DC to DC converter. As an overview, we will go through the project's general background, leading us to the problem statement, aim, and objectives. After that, we'll look at the solution development, its results, and some concluding remarks. An LLC converter is a DC to DC converter, and it consists of three main parts. Number 1, the bridge circuit at the input. Number 2, the LLC tank with a transformer. And number 3, the rectifier with a filter capacitor at the output. To understand the converter better, we note that the total gain of the converter is just the product of the gains of each part. Both the bridge circuit and rectifier shown here has a gain of 1, so they don't contribute anything. The transformer has a fixed gain according to its turns ratio, and most importantly, the LLC tank has a variable gain that we can regulate by changing the switching frequency used at the bridge circuit. LLC converters are used in many areas, including in PV systems as more people use them as the awareness for sustainability increases. For this project, we are focusing on the AC module inverter or microinverter as seen on the left, and specifically the two-stage type. In a two-stage microinverter structure, the front-end DC-DC stage, which is where our focus is on, functions to implement the maximum power point tracking or MPPT algorithm, and to also boost the PV's DC voltage up to around 400 volts, so that the DC-AC stage after it can invert it for grid connection. Working step by step, this project focuses first on taking care of the voltage boosting. A typical LLC converter's gain is regulated by varying the switching frequency Fs, and when a wide gain range is needed to accommodate a wide input voltage range, we are forced to use a wide Fs, which can lead to issues such as decreased power density because of larger magnetic devices, degrading the EMI performance, making the gate driver design difficult, etc. This leads us to our aim and objectives for this project. The objective focuses mainly on overcoming the wide Fs issue while achieving a wide voltage gain range. The control method developed at this stage focuses on regulating the output voltage at 400 volts. And finally, we will evaluate the performance of the system. After surveying the literature, I've settled on modifying the conventional LLC converter with multi-mode rectifiers, or MMRs, since it boosts voltage, consists mainly of diodes and capacitors, which are passive components, and has a simple control, just on or off. The slide shows the rectifier structure used, which is based on the work of Shang, Wang, and Cao. Using the two switches, they claim that the rectifier is capable of outputting 4, 5, and 6 times the input voltage, where the modes can be seen from their names. However, during my simulation, I found that the VFR injects DC current into the transformer, risking saturation. Therefore, I only used the MMR in its VQR and VSR modes, which times 4 and times 6 respectively. Next, we break down the input voltage range into two sections, based on the MMR gain values of 6 and 4, which gives us two sections, in which their gain range uses a switching frequency range that overlaps with each other, or at least that's the assumption. Thus, we can reduce the Fs range for attaining a wide input voltage range. From here, we can see the input voltage boundary at 22.5 volts, where we will have to switch between the MMR modes. And to reduce switching modes back and forth at the boundary, hysteresis is introduced by over-designing the required gain in each section. Using first harmonic analysis, the expression for the LLC tank's gain is obtained and is found widely in the literature and in the industry. However, it was derived assuming a full bridge rectifier was used, and even the source from which I took the MMR structure assumed this. The old expression proved to be unworkable when using this MMR, and thus, an original expression that accounts for the MMR's effect on the resonant tank gain was obtained and confirmed by a simulation that works on the symmetrical rectifiers used. This falsifies the assumption made in the previous slide, and as it turns out, for the same gain range, the switching frequency range will be slightly wider when we use the MMR mode that boosts higher, which is the VSR in this case. A closed-loop system was made with a Type 2 compensator, mainly basing on a method provided by an example in Plex itself. It functions very well to regulate the output voltage and has a quick response. It is also able to regulate the voltage even under no-load condition, which the conventional LLC converter couldn't. At the beginning of the simulation, the selection of the MMR's mode is based on the input voltage that we're at, whereas during its operation, it is changed when it crosses the hysteresis value. This slide shows the LLC converter modified with the MMR implemented in Plex, along with the controllers and measurements box around it. Here we'll take a look at a few significant results, first of which is the FS range. When using the LLC with full bridge rectifier, the FS range is from 63 kHz to at least 600 kHz, as the upper limit is not well defined at no load and increases indefinitely, even beyond 1000 kHz. When using the proposed converter, the FS range is reduced to be from 61 kHz to 120 kHz when considering the design requirements from 20 volts to 33 volts. However, slightly increasing the range by 3 kHz affords us a 50% wider input voltage range from 14.1 volts to 33.75 volts. Next, looking at the voltage stresses in the rectifiers, we see that in a full bridge rectifier, each diode and capacitor have to withstand at least the entire output voltage of 400 volts, whereas in the MMR, all diodes and capacitors withstand a lower voltage stress, the highest being half of the output voltage at 200 volts. Here we look at their comparative efficiencies, and unfortunately, we notice that the proposed converter has a lower efficiency overall, which is not surprising since it has more components. However, the main drawback arose from its LLC values that cause a large circulating current in the LLC tank, leading to a higher conduction loss. Furthermore, it must be noted as well that the switching loss was not properly accounted for, and the conventional LLC should have a poorer efficiency due to its switching loss, but is unfortunately not captured in the simulation and so also not seen here. For some concluding remarks, a few limitations are noted, including the usage of FHA for design purposes, which is the simplest but not the most accurate method. Thermal modeling was not performed, and thus the switching losses are not known, making the efficiency calculations less accurate. And lastly, the simulation still considers many things in the abstract, such as the LLC tank values and the compensator implementation. There are much more work to be done even after my project phase ends, such as to improve the LLC tank parameters in the design, to introduce a mode transitioning strategy for the MMR, such that the transition is not too sudden, and to implement MPPT algorithms and thus regulate the gain based on the input voltage. This project solution includes sustainable considerations as well, such as the reduction of voltage stresses on the diodes and capacitors when the MMR is used, increasing their lifespan and allows usage with higher output voltages. Furthermore, the primary inverter is still a full bridge circuit, and so conventional and/or alternate techniques to alter the converter gain based on changing the control signals can be used here as well. And finally, the transformer turns ratio was reduced from 1 to 50 to 1 to 3, making it more practicable and power dense. This is all from me. Thank you for your time.